Okay, so 11.4 has like one big topic, but in two different ways. And it is what happens if there is, if there's a horizontal asymptote or something like that, in which our graphs are going to continue on forever to the left and to the right. So we're not really talking about vertical changes or a vertical unbounded part, but a horizontal one. Okay, and then we're gonna bring back in sequences, if you remember, like your sequences and series, and we're gonna talk about how those would lead to determining a limit. Still limits, but in a different format. So this one says using limit. We're doing end behavior. We're gonna use limit notation to describe the behavior of the graph as it approaches infinity and negative infinity. And now we're talking about the x values. So when we're talking about end behavior, quick recap, if we're talking about like a polynomial function or something like that, and it was like an x squared, like let's say it said f of x equals 2x squared plus x minus 1, right? And I asked you what the end behavior was. The rule then is you look at the exponent. If it's even, that means they both rise or they both fall. If it's odd, they go in opposite directions. Do you remember this? Yes. So end behavior is what's happening on the left and the right of your graph. Literally the ends. The left and the right. Are your arrows both pointing up? Are they both pointing down? One up, one down, that kind of thing. So we're going to learn how to describe that using this limit notation. And the way we describe it is if I'm talking about left-hand behavior, so if I'm talking about what happens on the left side of my graph, then I'm saying the limit as x approaches negative infinity. Because negative infinity is where on my number line? It's to the left, right? And then if I'm talking about right-hand behavior, or the right side of your graph, then I would say the limit as x approaches positive infinity, because positive infinity would be on the right-hand side of the graph, okay? So that is how we describe end behavior. And then what we will say the limit is what's happening to the y's on that side of the graph. So if I look at the example that's here, if I go to the left of my graph, so if I keep going this way, because that would be left-hand behavior, my y values start high, right? But then they get lower, 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 lower. And they keep approaching the x-axis, but they're never going to touch it because there's a horizontal asymptote here. So if I was asking what y values is this closest to, you would tell me what? What's the y value at the x-axis? 0. So if there's a horizontal asymptote at 0, then the end behavior on that side of the graph is going to be 0. Does that make sense so far? And then if I was talking about the right-hand side of the graph, so if I'm talking about the right-hand side, I'm going to the right, my y values start high up here, and then they get lower and lower and lower and lower and lower and lower and lower, and they continue on forever in that direction, getting closer and closer to the x-axis, but never touching the x-axis. So I would describe that end behavior as it is approaching 0, okay? So the way we would describe this, if it asks for the end behavior of this specific graph, the notation would be like this. The limit as x goes to negative infinity, f of x equals 0, and the limit as x goes to positive infinity, f of x also equals 0. So on both sides of my graph is approaching the x-axis, but never touching it, but getting as close as you possibly can to it. So the limit notation would be that, okay? It does not mean it's the limit of the graph. It means it's you're using limit notation to describe the end behavior. Those are two different things, okay? The limit would be the y at a specific point. Okay, so example 1 says find the end behavior of the rational function. The limit as it's approaching negative 1, which would be the left, and the limit as it's approaching positive 1, which would be the right-hand side. Let's look at this graph, okay? What's happening on the left-hand side, right? It's getting as close as possible to this asymptote. It's underneath it this time, but it's still going to approach it. And on the right-hand side, that same asymptote, right? So where is this passing through? 1/2. So on both sides of your graph, f of x equals 1/2. Super easy. All you got to do is be able to identify the horizontal asymptote. If the graph's given to you, literally look at the graph, and then we're going to refresh on how you find a horizontal asymptote if it's a rational function. So we did this a while back. like the end of chapter 4, okay? But this says, if I have a rational function, which means there's a fraction, right? There's a variable in the top, there's a variable in the, or at least a variable in the bottom. It doesn't have to be a variable in the top, but at least a variable in the bottom. Then your horizontal asymptotes occur in one of these 3 ways. The numerator in the exponent on the numerator is less than the exponent on the denominator. Then your horizontal asymptote is y equals 0. If the exponent on the numerator is the same as the denominator, then it is y equals the leading coefficient of the numerator over the leading coefficient of the denominator. And if the exponent in the top is greater than the exponent in the bottom, then there are no horizontal asymptotes. So if I had f of x equals x to the second plus 1 over x to the second, well, let's do 3x to the second minus 1. Which scenario is this? N is less than m, n is equal to n, or n is greater than m?
N is less than m.
Nope.
Greater.
These are both 2's. I don't know if you can see that.
Oh, the exponent.
The exponents are the n's and the m's, right? They are the same, and if they're the same, this is the leading coefficient one, right? So the leading coefficient in the front and the top would be 1, leading coefficient in the bottom would be 3. So my horizontal asymptote would be at y equals 1/3. Yeah, sure. What if I said f of x equals 2x squared plus 1 and the denominator was 3x plus 1? Now what's the relationship between the exponents? Top is bigger than the bottom, and in that scenario, what's true?
Equals 0. I mean, not.
No horizontal asymptote. Remember, if it's 1 bigger, it's slant, and you can't have slant and horizontal. So if it's bigger in the top, there's no horizontal asymptote. All right, let's see if we could catch it this time. If it said 2x squared plus 1 and 3x to the third plus 1, what's true about it? Good. The exponent at the top is less than the bottom, so y equals 0 would be my horizontal asymptote. So because the horizontal asymptote determines the end behavior of this first graph, left and right, would be 1/3. The end behavior middle graph, it actually would not exist, which we'll talk about in a second. And the end behavior in the middle, 0. I mean on the right, 0, okay? All right, so use the limit notation to, or limits using the horizontal asymptotes. If the rational function has a horizontal asymptote, then the limit is, as the function approaches both infinity and negative infinity, is the horizontal asymptote. That's what we just did. If there's no horizontal asymptote, then the limit does not exist. Good? Because that curve would be unbounded. All right, example 2. Find the limit as it approaches theta if it does not exist. State D and E. So A, what's the exponent in the top? 1 in the bottom? 2, what's that relationship?
2.
It's less than, which means y equals 0 is my horizontal asymptote. So the limit as x goes to negative infinity, f of x equals 0. And the limit as x goes to positive infinity, f of x equals 0. And B, what's the exponent in the top? 1, exponent in the bottom? 1, what's that relationship? They're the same, so it's leading coefficient. It would be y equals -2, because this is 1 and this is -1. So limit as x approaches negative infinity and limit as x approaches positive infinity, f of x equals -1, f of x equals -1. So on web assigned, part of that's going to get filled in for you, like the limit as x approaches negative infinity, but make sure that you know how to write that from scratch. -2. Sorry, thank you. I don't know what I said at the beginning. Did I say -1 from the beginning? -2. One of the 3 scenarios. So top is bigger, doesn't exist. Top is smaller, 0. Top is equal, the leading coefficient. Yep. The same way you find the horizontal asymptote. The horizontal asymptote is the end behavior. Yeah. All right. C. Exponent in the top is bigger, 2 to 1. What does that mean about your horizontal asymptote? Does not exist. Now D requires some work. We have to make that one fraction. So you can't adjust it based on where it is right now. So these is when it gets a couple more steps. I would put this over 1, and then I need to give it a like denominator. What's the denominator going to be? X squared. So I multiply this by x squared and this by x squared, and I get 4 plus 3x squared over x squared. Now what's the relationship on the exponents? They are equal, which means my horizontal asymptote would be at 3. Good. 3 over 1. So the limit as x approaches negative infinity and the limit as x approaches positive infinity, both of these, f of x equals 3. Easy stuff, right? Good? Okay. The second part just pulls back in your sequences. So if you remember sequences, this is where you get given a little formula, and then if I want to find the first term, the second term, the third term, whatever it is, I just take those, plug them in. Plug in 1, plug in 2, plug in 3, plug in 4. Well, the behavior there, think about what you're doing. If I'm plugging in 1, then I'm plugging in 2, then I'm plugging in 3, then I'm plugging in 4, then I'm plugging in 5, I am constantly going to the right-hand side. Does that make sense? So I am actually, if I pay attention to that pattern, I am going to determine the end behavior of my graph on the right-hand side. So if I were to look at a graph, x is 1, x is 2, x is 3, x is 4, and I keep going, that pattern is going to lead to a limit. So you can either do it the way we did it if you understand your horizontal asymptotes, or you can do it this way. I don't care which way you do it. This one will say find the first 5 terms or find the first 4 terms and then determine the limit. Sometimes it's easier than others to figure out what that pattern is, but you can always fall back on your original rules about your horizontal asymptotes. God bless you. So it says find the terms of the sequence. Observe the behavior. As n increases without bound, the terms of the sequence get closer and closer to the L value, and the sequence is said to converge to that value. So it's that the language converge means what's happening to it. It's getting closer and closer to that behavior. That's what the word converge means, okay? All right. So we're going to find the first 5 terms in the sequence, and then we're going to use the terms to evaluate the limit of the sequence, and we're going to assume n begins with 1. We're going to do A like by hand, and then we're going to do B on the calculator because I want us to look at what happens. So I'm going to find A1, I'm going to find A2, I'm going to find A3, I'm going to find A4, and I'm going to find A5. So for each of them, I'm plugging that value in. 2 times 1 plus 1 over 1 plus 4. I get 2 plus 1, which is 3, over 1 plus 4, which is 5. Then I get 2 times 2 plus 1 over 2 plus 4. And I get 4 plus 1, which is 5, over 2 plus 4, which is 6. And I go to the next one. 2 times 3 plus 1 over 3 plus 4. 6 plus 1, which is 7, over 7, and that's 1. And then I go to the next one. 2 times 4 plus 1 over 4 plus 4. 8 plus 1, which is 9, over 8. And then last but not least, 2 times 5 plus 1 over 4 plus, or not 4, sorry, 5 plus 4. 10 plus 1, which is 11, over 5 plus 4, which is 9. So what's happening to these values? 3/5, 5/5, or 5/6, 1, 9/8, and 11/9. They are increasing, yes. If you're thinking about like if they increase without bound, for example, then it would be a drastic increase. You would start to see numbers jump a lot. These are not jumping a lot, right? But they are jumping a little bit, okay? They are starting at 3/5 and getting closer and closer to, now it says 11/9. If I kept going, okay, they're gonna keep getting just a little bit bigger. But if you use your rules about your horizontal asymptotes, what would you have said the horizontal asymptote is of 2n plus 1 over n plus 4? What's true about the exponents?
2.
They're the same, so it would be the leading coefficients, and we would say that horizontal asymptote is happening at 2. So I think it's easier to have both knowledge and kind of converge them like together, because I don't really have a clear pattern yet. I know it's getting bigger. I know it's not getting huge, but I would have had to keep plugging in points to see that it's going to keep getting closer and closer to 2, but it's never going to hit 2. knowing your rules about horizontal asymptotes is definitely going to help, okay? It eliminates a lot of work. So I know that I found the first 5 terms of the sequence. Now I'm going to use that to evaluate the limit. The limit as x goes to infinity and the limit as x goes to negative infinity, both would be 2. And usually if we're using the terms of the sequence, we're only putting in 1, 2, 3, 4, 5. You're only talking about the right-hand side of your behavior, but because we know what happens at that horizontal asymptote, we can see both.
So left-hand side would be like negatives?
Correct. Yep. All right, now let's plug in, but here it just said start with 1. So we did the first 5 terms that way. Okay, now let's plug in the bottom 1 into the calculator so you can see what happens. So grab your calculator. And we're going to make y1 2x plus 1 over x squared plus 4. Okay, so I put it in the calculator, and then I'm going to hit graph. Oh, my window is very off. Let me see. Hang on. I'm going to adjust my window. Negative 10, 10. Negative 10, 10. And I'm going to hit graph. All right, so it's definitely approaching that center line, right? That the y equals 0 line, if I look at the left-hand side and the right-hand side. If I wanted to get the terms in my sequence without having to do the work, I can literally just go to table, second, table, and I would go up to where x equals 1. So I'm going to start where x equals 1. Okay, and my first term is there. It's 3/5. So A, this time it's B. So B1 is 3/5, B2 is 5/8, B3 is 7/13, B4.
How do you get there again?
I hit, so I typed it into my y equals, and then I went second graph, and that's your table. And then I'm going to scroll down because I want 5. B5 is 11/29. Let's say I wanted to know those values in decimal form, like let's say I want to do it as a decimal answer, then you can actually force this to be in decimal form by going to your mode. If I go to mode, if you see it says answers, auto, DEC, if you go to answers and you change it to DEC, and I go back to the graph, and then I go back to the table, it's going to give you those values in decimal form, okay? So instead of having to convert, like if it wanted you to answer them in decimal form, now I don't have to convert them each one, okay? And sometimes it's a little bit easier to see, but as I go through these values, they're definitely getting smaller, right? No matter how high I go, they're getting smaller, 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 smaller. But no matter how high I go on that value, it's never going to cross through the 0, okay? Because look at the exponents. What's the relationship on the exponents on B? What's the exponent in the numerator? Right. Well, the one on the top is smaller than the bottom. So the horizontal asymptote is at 0. So limit as x goes to positive infinity and limit as x goes to negative infinity would both be 0. Yeah. Go back to mode and then put it on auto. Answers, auto. Huh? Is it stuck? Oh, okay. Questions on any of that stuff? So if you ever see like use the table feature on your graphing utility to find the following, that's what you're going to do. If it doesn't say that, then obviously you're plugging in. But we could save some time using that table.